Welcome to calculus. So we're going to look at series. If you haven't watched my video on sequences, I would encourage you to go watch that one first because we need sequences to understand what a series is. So go find that one and watch it and then come back to here. It'd be a nice little deviation for 11 minutes. So anyway, when we talk about a series, the series, I'll get my pen here, a series is the sum of a sequence. All right, that's really all it is just the sum of a sequence. So, and we have lots of ways we can write this. One of the most common ways to write a series is using sigma notation with some start value. I like to use K. A lot of textbooks use I and N as their values there, and going up to whatever N value of N that we want to use. Okay, this N can be a particular number or it can also be infinity. And then you have whatever your rule is right here, right? And a lot of times we write out the actual expression right there. Or another thing we can do is we can also, in generic terms, talk about this being some type of sequence that we put right here by just saying A sub n. That's a funky looking A, isn't it? There you go, so it's A sub n. So if we define A sub n to be 1 over n, and that's our sequence right there. So this is our sequence. Then our series for this exact same thing would be the summation from k equals 1 to wherever we want to go. We can just say infinity of 1 over n, which just simply means we got 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4, and it just keeps on going and going. Now, that's the basics of what a series is. All right, I've got my S there. There's the series for it, right? So there's the sequence, which is the individual terms. Okay, so this is each term, if you will, is the sequence, whereas the series is the sum of all those terms. Now, how is this useful to us? Well, it's useful to us in a lot of different ways. But the first and biggest thing is make sure you understand what we're talking about, as the sequence is a list and the series is a sum. Okay? Now, when we start digging in on this, we say, well, can we actually find this sum? Can we do the sum for this one? Because this is an important piece. And to kind of play around with the different aspects of this, I'll come, well, we can just do the sum first here, and I'll show you. So you got 1 plus 1/2, which is 1 and 1/2, right? And then plus 1/3 plus 1/4 on down the line, right? So then you do the next, and what this would be called right here, this first piece is what we call the second partial sum, okay? So this would be, if you just ignore everything after the third sum, this would be S sub 2. So S sub 3 would be that 1.5 plus the 1/3. So at this case, this point, you're talking about it being 1 and 5/6, right? Okay, so then S sub 4, which just simply means you take 1 and 5/6 and you add 1/4 to it. So you get a common denominator of 24 at this point, and you have, that's 20 plus, let's see here, right, 24, so that'd be, is that 2? So that would be 1 and 5/6, or 20 over 24, plus, let's see here, that'd be 6 over 24, so that'd give us 1 and 6/20 over 26 over 24, or 2 and 2/24, or 1/12, and you just keep on going, so you can then find the fifth sum. Now, what you're going to find about this one in particular is that you're not actually ever tending towards a particular value. You keep adding these values up. Now, I encourage you to pause the video for a second here and add this up. Do this one. So the next sum would be S sub 4, or 2 and 2/24 plus 1/5, right? And the next sum, the next partial sum, would be S sub 5, right? The one that you just found there, plus the next value of 1/6. And what you're going to find is that this value, this sum, it actually keeps on going off to infinity. You're never going to find a place where it starts getting smaller and smaller. That's not always the case. In some instances, you actually run into these situations where the sum is actually finite. Now that may seem kind of weird to think, well, you're adding an infinite number of pieces together and you can get an actual finite value, a particular number. Think of this box. So we already have the example where we add all the values together and it goes on forever. So here we have this box. The area here would be 1, right? Well, let's take the box, or the square rather, let's split it in half. So it's a square, so it's symmetrical. So now you have 1/2 plus 1/2. Well, so we're talking about this being 1/2 plus 1/2, which is still 1. Let's take that bottom half and we'll split it up. So that's 1/4 and 1/4. So you're actually talking about being 1/2 plus 1/4 plus 1/4, which is still equal to 1, right? And then let's take the one of these 1/4 sections here and let's split it up into 1/8 and 1/8, and then you can split that up into 1/16 and 1/16, and then split that next one up into 1/32 and 1/32. And how far can you take out this little thing? Now my pen, that's about as far as I can draw that out, but we can keep splitting that next section up into equal parts, taking half of it every single time. So you end up with 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32 plus 1/64, and on down the line. And this is going to be equal to 1 because we started off with it being the area like that, right? So think about what this a sub n would be. A sub n would be 1/2 raised to the n power, right? Here we're letting n equal 1, n equal 2, n equal 3, on down the line. Okay, so this would be your sequence here, right? What would your series be? Your series would be the sum starting off with k equal 1 going off to infinity of 1/2 raised to the n power. And we actually know, because of the way we started this thing off, that this sum is actually equal to 1, which means that this particular series converges. And what it means for it to converge is it means it goes to a value. Okay, it goes to a particular number. And what's really interesting, or what's really important to point out, is that these values, this sequence gets small fast enough. And a lot of people say, fast enough, what does that mean? Yes, that's exactly what it means. It means it does it fast enough. And what we're going to do over the course of the next several videos is we're going to look at different ways to determine whether it is doing it, whether those individual terms are getting small enough, fast enough, so that we are actually converging on a value as opposed to continuously growing. Like on the previous example where I said a sub n was equal to 1/n, that sequence was getting smaller. That sequence was going to 0. That sequence was converging. But that series didn't. The series just kept getting bigger and bigger and bigger. Here, this series, not only is the sequence converging, but so is the series converging, because the values are getting small enough, fast enough for them to go a particular value. This is one of these weird things that exist within our world of mathematics. Okay? Now, so we talked about the idea of partial sums, and we could do partial sums with this one. We could say s sub 1, which would be 1/2. S sub 2, the second partial sum, would be 1/2 plus 1/4, which would be 3/4. The third partial sum would be 3/4 plus the next piece, which is 1/8. So that would be, 7/8. And you could just keep on going with that, right? And figure out the decimal equivalent. And what you're going to see in this particular instance is that you're getting closer and closer to 1 as opposed to just continuously growing. I encourage you to kind of play around with these, rewind this, and rewatch these different components, deal with these different components and run them out yourself as many times as you need, because I think it's useful for you to kind of play around with the different types and just kind of see which ones do converge and which ones don't. Like, think about what other types of scenarios could we set up? Could we say that a sub n is equal to 1/n squared? How does that compare? What if we would compare that to some other one, say, let's say n raised to the second power? What does that one do? What about if we say c sub n is equal to n raised to the 0.3 power? Okay, a fractional exponent there. Another way would be thinking that would be 3/10. What do those things do when we start changing the way that those values are set up? And we can kind of compare all those. Sit down and look at the graph for these and compare the individual graphs. Remembering that we're not going to create lines. What we create is a series of dots, right? Because we're dealing with a sequence here rather than a function. And what do the functions do? And we can learn a lot from this just by doing those things. So I encourage you to get a graphing calculator or go to some type of cloud-based graphing calculator system and graph these different ones as if they were functions, so you can get an idea of what these sequences would be doing. And I can do these for you in front of you, but it's really going to be far more effective and useful for you to play around with these in lots of different ways on for yourself. So pick some values, and if you want a couple more to choose from, let's say d sub n were equal to 1/2 to the n power, which is one we already just did. E sub n, I'm just using different letters to denote different sequences here. What if it's 1/4 raised to the n power? Or what if it were, let's see here, what if it were 5/4 raised to the n power? Play around with those different values and see what those different values do for the series and what they do for the sequence. Okay? Take care. I hope this was useful, and keep doing math. Take care.